Hello and welcome to Database Management Systems. I'm Jyoti Christie, and in this video, I'm going to explain to you deadlocks in transaction management. So let's begin. First, we are going to see when a deadlock is created. So you can see this example on your screen. In this example, you can see that in T1 transaction, there are two transactions, first of all, which are T3 and T4. And in T3, you can see that there is an exclusive lock. An exclusive lock is taken on B, and then T3 is reading B, and then it's subtracting 50 from B, and after that it's writing B. Now notice that T3 has not yet unlocked B, and T4, which is there next to T3, that has obtained a shared lock on A, and then it is performing read A, and then it is performing a shared lock on B. So you can see this is the way T3 and T4 are working, and both the transactions together are holding one lock each at this point. So T3 is holding an exclusive lock on B, T4 is holding a shared lock on A. Now, look at the point where T4 is asking for a shared lock on B, and T3 is trying to ask for an exclusive lock on A. So obviously this is not possible because T4 is having a shared lock on A, and hence T3 cannot have an exclusive lock on A since they are not compatible. And T4 wants a shared lock on B, which is also not possible because T3 is already holding an exclusive lock on B. So even those two are not compatible. Now, let's see how you can prevent this type of a situation, because in that type of a situation, both the transactions get stuck and they cannot move forward, and that's why the system comes to a standstill, and you don't want such situations. So first we try to prevent such situations, and to prevent these types of situations, we employ some deadlock prevention techniques. The first one is known as a no circular wait technique. In this technique, before the transaction begins, it obtains all the locks on all the data items that it needs. So if the transaction knows that it's going to require data items A, B, C, D, E, then it's going to first obtain the locks on all A, B, C, D, E, and then it will begin. Otherwise, it won't begin. So either all the items are locked in one step or nothing is locked. So obviously the advantage of this is that there is no transaction waiting for another transaction. If suppose a transaction is not able to get all the locks on the data items that it requires, then that transaction will simply not begin, which means even the data items that it was able to lock, those data items also will be released. So that's an advantage of using a no circular wait technique. However, there's a catch, because no circular wait technique requires that you know beforehand what types of data items will be required. And most of the times, transactions do not know this beforehand. So the first disadvantage of no circular wait is that it is very hard to predict which data item the transaction will require from the beginning. And also, it leads to low resource utilization, because it's possible that I have a transaction that's going to take about 1 hour to run, and in the beginning it requires data item A, but it requires data item D after, say, 25 minutes. But it will still hold data item D for 25 minutes because it has to acquire the lock before beginning. And this leads to a low resource utilization because no other transaction will be able to access the data item D while this transaction is holding it. So that is the first technique of deadlock prevention. And it can be employed if you are able to predict which types of data items are needed, but obviously the resource utilization will be low. The next prevention technique is known as a wait die technique. So this technique employs the use of timestamps, where each transaction is given a timestamp, and it's very much similar to the concurrency control technique, which was based on timestamps. So if you watched that video, you would know that, but that's okay. We can see what it is about. So first of all, when a transaction Ti requests a data item that is currently held by Tj, so Tj is the transaction having a data item. It has locked a data item, and Ti requires that data item from Tj. So what happens in this case? Ti will wait only if it has a timestamp smaller than Tj. Having a timestamp smaller than Tj, which it means that Ti is older than Tj, which means Ti came first. So a transaction that enters the system first is always having a timestamp that is less than another transaction that enters afterwards. So Ti can wait for Tj to finish only if it is older than Tj, and otherwise Ti will be simply rolled back, which means it is aborted in order to prevent a deadlock from occurring. Now let's understand this better with an example. So consider you have three transactions, T1, T2, and T3, and they have the following timestamps, 5, 10, and 15. Now, assume that T2 holds some data item and T1 wants it. So T1 is requesting for a data item from T2. So as per the wait die technique, because the timestamp of T1 is less than the timestamp of T2, because 5 is less than 10, T1 will be allowed to wait. So T1 will be waiting. And you can see that in the wait die technique, the first word is wait. So the older transaction waits. Now assume that T3 requires a data item from T2. Now in this case, as per the wait die technique, the second part happens, which is die, which means because T3 has a timestamp that is greater than T2, which means T3 arrived after T2, so T3 is younger than T2, and that's why T3 will be rolled back. So T3 is going to be rolled back, which means it's aborted, started once again after some time. So that is the wait die technique. The first part of the wait die technique is to wait, and the second part is to die. So a transaction that is older waits, but a transaction that is younger dies. That is the wait die technique. The next deadlock prevention technique is known as the wound wait technique. So in the wound wait technique, if there's a transaction Ti that needs a data item from Tj, then Ti will be allowed to wait only if it has a timestamp that is greater than that of Tj. So that means Ti can wait only if Ti is younger than Tj. Otherwise, Tj is rolled back. So in this case, it is slightly different than the wait die technique, and I'll show you how with an example. So first of all, once again, consider three transactions, T1, T2, and T3, with three timestamps 5, 10, and 15 respectively. And now assume that T1 wants a data item from T2. So in this case, the timestamp of T1 is 5 and the timestamp of T2 is 10. So T2 is the younger transaction. So here the technique that is applied is wound. Remember, in the wait die technique, T1 would wait for T2, but in the wound wait technique, T2 will be rolled back. So it is also known as T1 wound T2. So that is why it is known as the wound wait technique. Wound just means rollback. So T2 is rolled back. Now consider that T3 wants a data item from T2. Now in this case, what will happen is T3's timestamp is 15, T2's timestamp is 10. So 15 is greater than 10. So in this, the wait part will happen, which means T3 will wait for T2 to finish, and then it will take the data item and do its own task. So that is how the wound wait technique works. the if there's an older transaction wanting a data item from the younger transaction, then the younger transaction will roll back. But if there's a younger transaction asking for a data item from an older transaction, then the younger transaction will have to wait. And this brings us to our last deadlock prevention technique, which is known as timeouts. So in timeouts, a transaction that has requested for a lock waits for a specified, at most specified amount of time. So if the time specified is, say, 10 seconds, then the transaction waits for 10 seconds. And if after 10 seconds also it does not receive the data item it requires, then the transaction will simply stop executing and release all the locks that it holds currently. So if the lock has not been granted within that time, then the transaction is set to timeout and it rolls itself back and restarts. This also prevents deadlocks. Now, most of the time, deadlock prevention techniques might help, but it's not necessary. Sometimes deadlocks will still occur, and most deadlock prevention techniques have a lot of rollbacks. So most people do not implement deadlock prevention in their system, since the transactions all perform some type of a job, and that job has to be undone because the transaction is rolled back. So to prevent such situations, sometimes we let deadlocks happen and then try to resolve them. So in order to do that, first we have to detect that a deadlock has happened. Your system needs to detect that there has been a deadlock. So for that, we create a wait for graph. And I've already explained what a graph is in a serializability video. So you can go ahead and watch that. A wait for graph essentially is a graph that shows which transaction is waiting for which transaction to finish. So it looks something like this. Now in this graph, you can see that there are several transactions. You have T17, T18, T19, and T20. So you can see there are arrows going out from T17 towards T18 and T19. This means that T17 is waiting for T18 and 19 to finish their work because it requires a data item from both of them. Below you can see T19 is having an arrow that is going out towards T18. This means that T19 requires a data item from T18, and that's why it is waiting. And there's also an arrow going out from T18 towards T20. This means T18 requires a data item from T20. So this is a wait for graph. Now observe that in this graph, there are no cycles. You can see that these two arrows are going outward, and that is why it's preventing a cycle from forming. So a wait for graph that has no cycles within it shows that there is no deadlock in the system of those transactions. That means these four transactions together are not deadlocked. Now let us see a wait for graph with a deadlock. So consider this wait for graph. Here you can see that there is a deadlock between T18, T20, and T19. It is forming a cycle. So due to that, this is having a deadlock. But you wouldn't say that all four transactions are deadlocked. You would say that only 3 transactions are deadlocked because there's a cycle only between T18, 19, and 20. So once we have detected which transactions are causing the deadlock, we then need to figure out how to solve the deadlock. So in order to recover from a deadlock, we need to obviously restart one of the transactions. For example, if I take say T19 from here and I decide that I want to stop T19, I want to restart T19. So when I restart T19, T19 will release all its resources, and whichever transaction requires resources released by T19 will get those resources. So T18 will get the resources of T19, and because of that, T20 will get the resources of T19, and because of that, T20 will be able to finish its execution. And once T20 is over, T18 can get the resources from T20, and so T18 can also finish its execution. So this is how you can resolve a deadlock. But there are certain rules when it comes to picking the transaction required to resolve a deadlock. Let us see that. That is known as deadlock recovery, where the first step involves select a victim. So this is where you will select a transaction to be rolled back. So several aspects are considered while selecting a victim. The first one of which is how long the transaction has computed and how much longer it's going to compute before it completes its designated task. So a transaction that has really worked for a really long time, you wouldn't want to just roll back such a transaction and ask it to do all its tasks once again. And also, if a transaction has still a long way to go, then you might want to pick such a transaction. And the second thing considered is how many data items the transaction has used. So if a transaction is holding a lot of data items, then the advantage is that if you roll back such a transaction, many other transactions who are waiting for this transaction's data items will get those data items and will be able to finish. But then at the same time, if this transaction starts again, it's possible that it will never be able to get the same data items back because they are held by someone else. And so it's a tricky question here also, but you need to consider all these things and then decide which transaction will be the victim. Next, we also see how many more data items the transaction needs. So based on that also, we can decide whether or not to roll back the transaction. And the next thing is how many transactions will be involved in the rollback. So this is like a cascading rollback that I explained a while ago. A cascading rollback is where one transaction depends on another transaction, and then another depends on this one. And so if one transaction is rolled back, then others also have to be rolled back due to it. So you have to take care that you're not selecting a transaction that's going to cause a lot many transactions to roll back. And so all these points have to be taken care of while selecting a victim. Now, once the victim is selected, the next thing that you need to do is to roll back. So rollbacks are of two types. One is a total rollback where you just, stop the transaction completely and start right at the beginning. Another one is a partial rollback. So if you do not want that all the work done by the transaction is destroyed, you can perform a partial rollback wherein you can roll back a transaction only up to a point which resolves the deadlock. So maybe there's a data item D that is causing a deadlock because it's held by this transaction. So you can just roll back the transaction up to the point where the transaction obtained a lock on D. And that will resolve the deadlock and everything can start functioning normally. And your transaction will not have to do everything again. It will have to do only some of its tasks again. So these are the two types of rollbacks that you can do. And this is how deadlocks are handled or resolved in the system in database management systems. And that's it for this video. I'll see you in the next one. Thank you for watching.